Okay, so we're going to be working with the personal loan analysis database. And the goal here is that the bank wants to convert its deposit customers, the customers that have checking accounts, into loan customers. So we're going to pull in these two very critical libraries, tidyverse, which is foundational for data science, and then Caret, which does classification and regression trees. And we're going to be using the create data partition function from Caret. So we're going to go ahead and read the data using read.csv. And if we look at the data set, we see all of these parameters. And the key one that's going to be for us is personal loans. So let's take a look at that. Here's a summary of the data, always good to look at the summary statistics to get some intuition of what's going on here. For example, education is 1, 2, and 3, it looks like, and we'll have to understand that better. And then this will become important because we're actually going to change one of these things, the personal loan, because it needs to become a factor so that we can do categorization. So here's a description of the attributes. So the personal loan, that's the key, is how it responds to a campaign, how the person responds to a campaign. So 1 is yes, they got a personal loan, 0 is no, and so we want to convert more people to them. And then you can look at everything else, like does the customer have a CD account, does the customer use internet banking, does the customer have a bank credit card, CC average, the average credit card spend, and then you see education, 1 corresponds to undergrad, 2 to grad, and 3 to professional. So we'll be converting that as well. Okay, so the first thing we're going to do is we're going to eliminate ID and zip code because we're not using that. And so it's always useful to do that. So delete all of the stuff, all of the columns that you're not using. So you see that ID is gone and zip code is gone. Okay, then the other thing that we're going to do is we're going to turn personal loan and education into factors. And it's very easy to see how this works. So we use mutate on the data frame, and we create this factor called education, and the levels 1, 2, and 3 correspond to the labels undergrad, grad, and professional. And then for personal loans, 0 and 1 correspond to no and yes. So we're basically mapping 0 to no and 1 to yes when we do that. And so when we look at the database now, you can see, for example, education, undergrad, grad. And then critically, personal loan, whether or not they're responding to our personal loan offer is now no or yes. Now, the first thing we need to do is partition the data set to prevent overfitting. And we're going to put 60% of the customers in train and then the remaining customers in the holdout. And so we use this function called create data partition from Caret. So we're just going to look at bank personal loan, and we're going to look at bank personal loan because that's what we're predicting. And we want it to be even in both the training set and the holdout set. We're going to say that 60% of them are going to be in the training set. And so we'll go ahead and run that. And here we can check to see if this has gone well. So let's look at bank DF. Okay, so that's 5,000. And then since we said that 60% of them were in train, that should be 3,000, which is correct. And the remainder should be in holdout. So it's 2,000. And now we want to create and plot our classification tree. So personal loan, it's going to be a function of everything, all of the other parameters. The training set is the train DF, and then the method is the class. Okay. So we run that. And then we're going to go ahead and plot. Okay, so here we see it, and we can just intuitively look at this. So here we get a yes, and we're getting a yes for people who are relatively high income and who are not undergraduates. So they're grad or professionals. Okay, and so that makes sense, right? So higher income people and later stages of education are more likely to take the loan. Okay, and then here we see the rules, and again, you should be able to map the rules to the visualization, right? These two things are identical technically, right? The rules are the same as the decision tree, just a different visualization. Okay, so now we're going to get a deeper tree, Okay, so here we're going to set what's called the complexity parameter and the minimum split parameter, which is basically going to go all the way down. So you see that in this tree we have some misclassifications here at the bottom where we don't keep splitting after a certain point. So we have like 22 and 5 and 32 and 6 and 5 and 18. Here we're going to go all the way down in order to illustrate overfitting. So you see here we now have 45 different leaf nodes, whereas in this one we have far fewer. This is a leaf node, this is a leaf node, so like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 leaf nodes. Here we have 45 leaf nodes, right? So a much bigger tree. And so it's so big that when we visualize it, we can't even see what's going on. Okay, so now what we're going to do is we're going to use a confusion matrix, which is a very, very valuable way of looking at performance for classification. It's basically the standard way, because you can get all sorts of parameters from it, like all sorts of metrics like accuracy, recall, precision. You can all get those from the confusion matrix. So what we're going to do is we're going to predict the training set, and then we're going to run the confusion matrix. And so there's a lot of data that's produced here. We're only going to look at the confusion matrix itself and the accuracy. So we see that the accuracy on the training set is 98%, 99%. Now we're going to look at the holdout data, and we see that the performance basically doesn't change, right? It's both 98 and 99%. And that was on the small tree, the first tree that we created with 10 leaf nodes. Now we're going to look at the deeper one, and this is the one that goes all the way down on the training set. So we should expect perfect accuracy, and we do in fact get perfect accuracy. But now when we run it on the testing set, the holdout set, we go back to our 98.5. Right, so this illustrates that the bigger tree is not always the best tree, and in fact, given the choice between these two, we would choose the smaller tree because it's a lot easier to interpret and it has the same performance.